Okay, last time we just finished solving this problem, and because it's kind of important to understand, we're going to kind of go over it again. All right? Okay. So we say naturally occurring chlorine. That means chlorine in nature. So if you go out in the world and you look for chlorine atoms, you'll find that when you find a cluster of chlorine atoms, they will be made up of a mixture of chlorine 35 and chlorine 37. Now, here's a little bit of a review question. When I say chlorine 37, what does the 37 mean?
There's 37 protons.
That's a good guess.
Oh, protons and neutrons.
That's right, protons and neutrons. Now, how can we remember that? How can the periodic table help us remember that? If I say chlorine 37, if somebody says chlorine 37 and you think, wait a second, what does the 37 mean? I can't remember. How can the periodic table help me with that?
Because if you find chlorine, it has a number on the top left, and that's how many protons there are. And if there's a lot, if there's the same amount, if there's a little less, that means it's protons and neutrons.
That's right, because the 17 is less than 37. That means the 37 must be that reminds us that the 37 is the protons and the neutrons. Very good. Now, if I say chlorine 37, how many neutrons is in an atom of chlorine 37? How many neutrons?
20.
20. That's right. Very good. So, here we have a mixture of chlorine 35 and chlorine 37. And we were told that there was 75.77%. Now, the term percent means out of 100. So, somebody had a bag full or a hat full of chlorine atoms, right? And they were pulling them out one by one, and they were finding the masses of those chlorine atoms. And some were chlorine 35, which has a mass of 34.9689. And some were chlorine 37, which has a mass of 36.9659. 75.77 out of every, in terms of percentage, so out of every 100, were 35. 24.23 were out of 37, or were 37, chlorine 37. So we decided that we would find the average mass by, instead of making a list of 35, right, instead of writing down all the numbers 35, 35, 35, 75 times, we'll just say 35, or actually 34.9689 times what?
37.
No, the 75 points times the 75.77, because that's how many times you'll see it in the list. And then we add that to what?
Where is it? 37.
36.9659, right? The mass of the chlorine 37.
9.
Times what?
That's 36.
No. Times the 24.23.
Times 24.23.
Okay. Then we have to divide all of that by what to get the average?
2.
Nope, divided by 100, because there's not just 2 atoms. There's 75.77 out of every 100 of this kind, and 24.23 out of every 100 of this kind. So we divide it by 100. Right. And then when we put that in the calculator, we found that our answer, if we put this in the calculator, last time we actually put 35 and 37 here. But these are the more precise numbers. exact numbers, and so we get out of this 35.45. Okay. So here's another one. Here's another one. Let's see if we can solve this one together. There are two isotopes of an element, some element Z. The first is 56.5% in abundance and has a mass of 152.3. All right. If the atomic mass is 155.5, what's the mass of the other isotope? All right. So we have to set this up very, very similar, the same way, but this time we're not looking for the average mass. They've told us that the average mass is 155.5. So I'm going to write that down here. The average is 155.5. That's what we were looking for last time. And this time, we want to find the percentages of the two different isotopes, add them together, and again, divide by 100. All right. Can you see the mass and the percentage of the first isotope?
56.5%.
Very good. 56.5%. And what is the mass of that isotope?
152.3.
Very good. 152.3. Excellent. Now, we need to fill in the rest of this. Now, did they tell us the percentage of the other isotope?
No.
They don't. But is there a way we can know?
Yeah.
How?
100 minus 56.
Very good. Minus 56.5. So it's 43.5. So 43.5% can go in here. And then the other isotopic mass can be solved for there. All right. So this takes a little bit of algebra, and I'm not going to go over it with you right now, but you just have to multiply both sides by 100 to get the 100 out of here. And then you're going to subtract the product here from both sides. And then you're going to divide by 43.5, and you'll be able to get the x, which ends up being 159.7. Now, what is that x again? 159.7. What is it we solved for there?
The mass?
That's right. That's the mass of the other isotope. Excellent job. Way to go. Okay, so here's another example. An element has an isotopic mass of 15.987. The mass of one of the isotopes is 15, while the mass of the other isotope is 16. Okay, so we have two different isotopes. What are their masses?
15
Yeah.
and 16.
Very good. 15 and 16. Now, the element has an atomic mass, that means on the periodic table, right, of 15.987. 15.987. What does that mean about the natural abundance of the isotopes? If the average is so close to 16, then it means that there's more of which one?
It's 16.
There's more of 16. So that means the abundance of X is less than that of Y. Right? Because if there's more 16, then the average is going to be closer to 16. If there's more 15, if there was more X, then the average would be closer to 15. If it was exactly half and half, 15 and 16, what would the average be?
50%.
It would be 50%, and the average mass would be right in the middle, right? Which would be what?
Oh, 15.500?
That's right, 15.5. 15.5. Very good. Excellent. All right, so let me tell you a little bit about the history of the periodic table, okay? As people explored the different elements and realized that, initially they thought, oh, there's water, it's an element. There's dirt, that's another element. Fire, right? And so they were growing and learning about the reality of things and recognizing that some things are compounds, like water, and some things are truly elemental, meaning you can't use chemical techniques to break them up. Okay? And as they discovered electricity, this helped a lot because with electricity they could add and remove electrons to compounds and those elements would pop off, would come off. So they began to find elements that behaved very similar to each other. And they realized, wow, if I am looking for an unknown element, but I know it's very similar to this other element, then it will be really easy to learn more about it. And so they quickly recognized that a table that could have all of the elements, and besides, I mean, it's very interesting that you think about the periodic table. This is all of the Legos that there are in the whole world, right? These are the true Legos. This is it. You don't have anything else to work with out there. Now, you can make a lot of different things from these, and that's what's, so phenomenal, amazing. But if you understand these materials, how they react and how they behave, then you can know the physical possibilities of this nature, right? Of nature, what we can and can't do because of the limitations of the periodic table or the elements. So Dmitri Mendeleev was given most of the credit for inventing the periodic table. However, there were lots of people involved in the process. But what he did was he began to organize the elements that were known, and his organization allowed him to predict certain elements' properties, even though they hadn't discovered the elements. And then as people began to discover elements and see that his predictions were correct, he was hailed as an ingenious and given a lot of credit for the periodic table. So our periodic table, we separate it into columns, right, going up and down, and rows going across. We also can call these periods going across and groups going down. We also refer to them as families going down. And there are some popular families of elements, popular columns, and we'll introduce those to you here. The whole periodic table can be separated into different groups. We have the first two columns here. Let me bring up the periodic table so I can show it to you as we talk about it. The first two columns here are our, the first two columns here and the last 6 columns of this main group are called the representative elements. Representative elements. Okay? And they say that, they call it that because there are a lot of rules that can be represented by these elements. You might have heard of the octet rule if you took chemistry before. So there are a lot of nice rules, easy, clean-cut rules that these 8 columns, the first 2 and the last 6, can represent well. So they call them the representative elements. And Dimitri's first periodic table was really just these first 8 columns. This blue section here is known as the transition elements. Transition elements. And it doesn't keep some of those representative, or those rules, it doesn't represent some of those more common rules that we learn in high school chemistry very well. But we gradually learn their chemistry and how they behave in this class a little bit as well. And then we have the inner transition metals, down here on the very bottom. Okay? So, we want to kind of begin to recognize those groups so that we can refer to them and use them and learn the properties. Okay? The modern periodic table has our elements, our inner transition elements down here on the bottom. But in reality, if you were to take the periodic table, it would look like this. Okay? Long time ago, people decided we're going to use 8.5 by 11 pieces of paper, and so the periodic table has generally been represented like this. Also, this huge space for these inner transition metals, which are actually, not discussed a lot in these types of general chemistry classes. And we'll also talk about how, or you can see here in this slide, some of these elements are man-made, meaning we took smaller elements and we collided them together. This isn't chemistry, this is physics, where we just ram them together really hard, and what happens is sometimes they stick and it results in a larger atom. Now those atoms don't last very long. Usually they degrade back down into smaller atoms. And this isn't chemistry, this is physics and nuclear decay, and we'll talk a little bit about it if we have time at the end of this semester or this section, these chapters. But in general, anyone up here with parentheses around the atomic mass. So you see, for example, all of this row down here has parentheses. These ones down here, down the very bottom, some of them are in parentheses. These are ones that were made in labs, and that's also why their names kind of correspond to things that you might have heard of, like ES is called Einsteinium because they named it after who? Einstein, that's right. CF is called Californium. What were they naming it after, do you think?
California?
Yeah, the University of California system. That's right. BK, have you ever heard of Berkeley? It's a town in California where the University of California, Berkeley, they have laboratories, and they're in collaboration with other laboratories that work on identification of different metals, or different elements, right? So you got lots of different elements here that were named after people sometime. This is after the Lawrence Livermore laboratories, Lawrencium, Nobelium, right? So Mendeleev, another Fermi, other popular figures in physics and chemistry. So America, right? Americium, Curium, named after Marie Curie, who was instrumental in discovering nuclear physics. So we got lots of different elements, but even of all these elements, or Legos I like to think of, that we have, a lot of them really aren't available to make things. All these ones in the parentheses aren't really available for us to do a lot of stuff. There are some exceptions, but that's pretty much the case. Okay, now this staircase we talked about before. Let's see if you remember. What does it separate, that staircase? Do you remember?
Metals and non-metals.
Very good. And the non-metals are here on the right. What's the one exception? Do you remember?
Hydrogen.
Hydrogen. Fabulous. So most of these elements, all of them, most of them are what? Metals or non-metals?
Metals.
Metals. And this little staircase here are our metalloids, except for aluminum. And you can remember that pretty well because we drink soda pop out of aluminum cans. We know that that's a metal. But the metalloids play a critical role in the development of this world as well, right? Our ability to use computers, really, we learned that from metalloids. All right, so can you look through this list and find out which one of these is correct? All right, I'll bring up the periodic table so we can kind of look at it. Is copper a representative element? Oh, there's one thing I didn't mention thoroughly here that I need to mention as well. The popular families. There's 3 or 4 really popular families. And remember, families are the columns, right? The alkali metals. These metals, if you put them into water, they will cause an explosion, and the resulting water will be alkali. Now, alkali is the opposite of acidic. Now, people have heard of the term acidic, and they know what it means in terms of pH, but oftentimes that's it. But alkali is the opposite of acidic. When we come to later chapters, we'll talk about what alkali and acidic means. But these are called the alkali metals. These are called the alkaline earth metals. These last two columns are also very popular. The second to last is called the halogens. The halogens. Fluorine, chlorine, bromine, and iodine have interesting properties which allow us to understand how matter and material work. So we often refer to the halogens. Our other column here is our noble gases. Now, noble gases, helium, neon, argon, krypton, xenon, right? They don't like to perform chemistry very much. They don't interact with other atoms. They have the magic number of electrons and the magic number of protons, and they're extremely stable. Usually, everybody else on the periodic table will interact with each other or other elements in hopes of attaining this number of electrons around themselves somehow. And we'll talk more about that in the future. Okay, so we got our noble gases, our halogens, our alkali metals, and our alkaline earth metals. Now we can better answer this question. Whoops, did you see the answer?
No.
Oh, good. So, which of the following is correct?
Where's F?
Where's F? I think it's number 9.
And F isn't right.
F is what?
Not right.
It's not because it's not a halogen?
Yeah.
Which row was the halogens? Or which column?
The green?
No. It was pointing to this one right here. It's too small to see for you probably. Let's go back and see which ones the halogens were.
Oh, it is a halogen.
It is a halogen. Very good. So we found the answer. Fluorine is a halogen. Carbon is a nonmetal. Sodium is an alkali metal, not an alkaline earth. Copper is a transition element. Okay, very good. So let's look at some of these properties of elements. All right, let's look at some of these properties of elements. Metals. Metals, you probably, think about having a good familiarity with metals, and we do, but most of the metals that we interact with are mixtures of metals, which we call alloys. And we don't talk a lot about alloys in this class, but our mixture, even our jewelry, most of our jewelry, almost all of it, is alloys. So this is not actually all gold. It's a mixture of gold with some silver and copper and other elements, iron. And the reason for that is if you have a pure metal all by itself, it becomes very malleable. So watch this video here of this person breaking up a piece of metallic sodium. See how it's almost like a tough clay dough, and they're using a chisel there, and the metal is very malleable. It means it can bend and kind of break, not shatter break, but be kind of broken apart relatively easily. Okay, so pure metal has this property. Now you'll notice also with this, when he's working on this metal, that there's an outside white layer on this sodium. And that's because sodium is an alkali metal and very reactive with water. And this piece of sodium here is reacting with the water in the air. And so they have to keep it in this desiccator, keeps it nice and dry. There's some material on the bottom here that absorbs water, keeps it nice and dry, get a good seal on there. All right. I showed you a video previously of putting some sodium into water. Let's watch this video here where the sodium goes into the water at night. Good snap. Does that remind you anything about the 4th of July or something?
Yeah, it looks like a firework.
That's right, and a lot of fireworks are made of metals like sodium or potassium, which are very reactive.
That was 150 grams.
Wait, is that tree on fire?
Oh, perfect.
No, it's a little bit of sparks somewhere from the sodium still sparking away. So what we just saw was people putting sodium, here's sodium over here, right? It's element number 11. People putting sodium into water. If you put sodium into water, it blows up like that. If you put potassium into water, it blows up even more. And rubidium even more, and cesium even stronger. Lithium also will blow up. And this is one of the reasons why lithium-ion batteries, for a while and still a little bit, we need to take care in how we use them in different devices. There have been times that new devices come out that have lithium-ion batteries that catch on fire too easily. All right, so lithium has some reactivity towards, towards moisture in the air, and the heat from that can result in fires. Same thing with planes. Airplanes, they used to put lithium-ion batteries in the devices in the planes, and they had to be really careful about that. And now it's limited the amount of lithium-ion batteries that can be shipped on planes, right? There's concerns and limitations for these things. So let's watch these videos now of people putting not sodium into water, but rubidium and cesium, okay? Let's watch these videos of this guy putting rubidium and cesium into water.
And watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody, this one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone.
Yes! That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave it to it. Good luck.
Thank you.
Okay, John, go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion.
And it does.
All right. So, an example of how, as you move down the periodic table, there's very similar properties, and in this case, we increase reactivity as we move down the periodic table from sodium, rubidium to cesium. Okay? All right. Very good. Nonmetals. Nonmetals. So one more thing about metals we want to talk about is their conductivity. Conductivity. And this means they can conduct electricity. All right? Conduct electricity and heat. And that's why a lot of our pans that we work on the stove with are made of metal, so that the metal can transfer the heat into the food easily, as opposed to absorbing it and preventing the heat from coming on the other side, right? Ice chests are not made of metal, because if an ice chest is made of metal, the outside will get cold and the heat will transfer out away, and therefore, or in, I should say, the heat transfers into the cold and warms it up very quickly. Mercury here is the only metal that's liquid at room temperature. All the other metals are solid at room temperature. Nonmetals. Nonmetals are brittle. So if you take them and try to break them, they'll shatter into kind of like what you would see as a salt, maybe like sodium chloride, little tiny powdered crystals type thing. They don't conduct heat or electricity. Many are gases, right? Few are solids of these nonmetals, and bromine is the only liquid at room temperature. You can change the temperature and adjust and get these nonmetals to become gases, liquids, or solids. But at room temperature, bromine is the only one that's really a liquid. They like to react with metals to form ionic compounds. Remember that, ionic compounds?
Yeah.
How can we generally know if it's an ionic compound?
It has to have metal.
That's right. A metal and a nonmetal come together to form an ionic compound. Excellent. Metalloids have interesting properties. They can behave like metals or sometimes behave like nonmetals in terms of their properties if you treat them slightly differently. So we learned to create computers. Computers store memory with silicon early on. I mean, relatively early on in our computer learning days, right? And that was because if we applied a voltage to silicon, then it behaved like it was conductive, whereas if we didn't apply a voltage, it behaved like it was non-conductive. And so with that way of differentiating whether the silicon was conductive or non-conductive, we made a way that we could store information in the form of conductive 1 or non-conductive 0. I might have switched those, I can't remember. But the point is, that's how computers began, and that's how still the model that we keep, where we have one on and one off, ones and zeros, and we store data in that way. But chemistry is catching up to the computer too. Someday we're going to have what are called quantum computers, where data can be stored not just as ones and zeros, where there's 2 possibilities, but we can have multiple different possibilities as molecular computers come along. Computers that store data in the form of molecules, so you can have data stored in multiple ways. And this will really increase the amount of data that we can store and how fast computers can run. There are other limitations that materials, even if they can run very fast, the materials transfer heat so quickly that they get too hot. They transfer information so quickly, electrons so quickly that they get really hot and begin to melt. And so there are other properties that need to be overcome, but someday we'll be able to improve computers, continue to improve computers greatly because of our understanding that initially came from these metalloids. Now, ionic compounds. Let's talk a little bit more about ionic compounds. Ionic compounds, like we know, are mixtures of metals and nonmetals. Okay? They come together to form new compounds. And when this happens, the reason why the metal and the nonmetal come together is because of their location on the periodic table, if you think about it that way. For example, chlorine. How many electrons does chlorine have?
17.
17 electrons. And notice that it's really close to a noble gas. A noble gas, right? The noble gases, I'm going to draw this noble gas here. Argon. It's noble. It has a crown, and everybody thinks it's so popular. Why do they like noble gas so much? Because it has the right number of electrons and protons, right? Now, chlorine is generally not happy about that. It wishes it had the same number of electrons as argon. Now, this isn't really true. Chlorine doesn't have any feelings like this. But in terms of stability, if chlorine can gain an electron, it can gain stability and have what we call a noble gas electron configuration. Okay? So why have I drawn him as sad?
Because he wants to be a noble gas.
And what is he going to do to attain a noble gas electron configuration in terms of his electrons? What does he need to do?
He needs to gain an electron.
That's right. He needs to gain an electron. Let me introduce you to another element. This is a metal, but sodium is also sad. I'm going to put the sad face right there. Why do you think sodium's sad?
He wants to be a noble gas too.
He wants to be a noble gas too. Which noble gas could he easiest for him to become like?
Where's Na?
Which one?
I can't find Na.
Oh, sodium is over here. It's number 11.
Oh, he's closest to Ne, neon.
And neon. He's closest to neon. But he's sad because what does he have to do to become like neon?
Give up an electron.
Give up an electron. That's right. Metals over on this side of the periodic table need to lose electrons to attain noble gas electron configurations. Non-metals over here on the periodic table need to gain electrons to attain a noble gas electron configuration. And so that results in so many different ionic compounds. So many different ionic compounds that'll be formed when sodium, for this example, right? What is sodium going to do for electron?
Give it up.
Give it an electron, that's right. And chlorine is going to take that electron, and so what we get is we get sodium reacting with chlorine to form sodium that loses an electron. Now, when it loses an electron, it doesn't lose its protons. So this sodium atom, how many protons does this sodium atom have? Do you know?
10.
Protons?
No, 11.
11. It has 11 protons. And how many electrons does it have before it gives one up?
10, 11.
It has 11 electrons also. 11 electrons. 11 protons and 11 electrons. But when it gives up an electron, it still has 11 protons, but now it has how many electrons? 10. It has 10 electrons. That's right. So because this number is no longer the same, it has 11 positive charges, but only 10 negative charges. So it has one extra positive charge. And so we write that there. There's an extra positive charge. So what is that going to make chlorine if chlorine takes the electron?
It's going to make it have 18.
It's going to have 18 electrons. 18 electrons. How many protons is it going to have?
17.
17 protons. And so the result is not a positive charge, but what? What do you think?
Negative.
A negative charge because it gained an electron. And so when this transfer of an electron occurs, the result are what we call, and this is what we call an atom that doesn't have the same number of protons as electrons. We call that an ion, an ion. And that's where the term ionic compound comes from. So these two ions come together and form an ionic compound. All right? So an ionic compound, we have been saying we can recognize an ionic compound because it generally contains a metal. But a better definition for an ionic compound moving forward is a compound that is made of ions. All right? So an ionic compound is a compound made of ions. All right? Now, that wasn't very helpful before to describe an ionic compound because we didn't know what ions were. But now we know that an ion is a compound, an element that has a different number of protons than electrons. And we also see here that ions can come as positive ions or negative ions. Now we can understand what it means to be an ionic compound or a compound made of ions. Now, we also want to be able to identify ions as either positively charged or negatively charged by their appropriate name, or we want to have a name for them. So positively charged ions we call cations. And that might make you think of a little cat ion. Negatively charged ions are called anions. Too bad they're not called dog ions. It'd be easy to remember. But they're called anions. All right? All right. So I have a little joke to help you remember that. Okay? It's not a very good joke, but it's a joke, and maybe it'll help you remember. So there's a dog and a cat, and they're in a restaurant. And the dog goes over and sits by the cat in the restaurant. And the dog says, "How are you doing today?" And the cat says, "I'm sick." And the dog says, "Are you sure?" And the cat says, "I'm positive." What does it mean when the cat says, "I'm positive"?
It's a positive ion.
That's right. The cat's a positive. It's a cation. Very good. So it's a silly joke, but what we really want to get is we want to be able to identify and remember that cations are positively charged and anions are not positively charged. Again, too bad they're not called dog ions, but with cations are positively charged. All right. So, for example, if I have this cation, iron with a +3 charge, and this anion, oxygen with a -2 charge, and I want to form them, bring them together in an ionic compound, all right, I can predict how they'll come together because of their charges. All right, and we'll talk about this next time. This is a good place to stop. All right, good job today. Thank you very much.
Bye.
Bye.